Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on applications of vectors. Now, this is actually our 5th lesson in our chapter for applications of trigonometry, and this is the exact same lesson that I gave to my students within the classroom. So what we're going to learn in this lesson is basically how to apply the dot product as well as determine the resultant vector from a word problem. And this is a fairly basic lesson. I know I can go in a lot more in depth, but because this is such a large chapter and a lot of the content is out of the scope of my class, we kind of keep things basic for this section. So I kind of start right in with the dot product. And again, I don't go into much detail for our class. We just kind of present them with the material and we just kind of practice it. So therefore, when they have to go out and apply the dot product later, it's something that they have seen. So the dot product is basically going to, it's not vector multiplication. It's basically going to be when you have two vectors, it's the product of the horizontal components. You can see U1 and V1, as well as a product of the vertical components, which would be U2 and V2. And you add those up and what you're getting is actually a scalar. And then some really cool videos that you can see like how that works with the vectors. But because I don't want to spend too much time as far as explaining and understanding dot product, I just want to make sure that students understand what it is we are trying to find and as well as how to find the dot product. Now, the important thing about the dot product is when the dot product is equal to 0, then that means that your two vectors are going to be orthogonal or parallel, which I'll get into in a second. When the dot product is positive, that means the two vectors face the same direction. And if they're negative, that means they're going to be facing in opposite directions. So those are just some things that you can see. And again, there's some great, kind of videos, tutorials where you can kind of understand a little bit more of the dot product, but it's just a little bit beyond the scope of our class. So I'll just say orthogonal. All right, so the next thing about the dot product, which helps us then, is it helps us determine the angle between the two vectors. So if we want to determine the angle between the two vectors, we can use this formula, cosine of theta equals the dot product of u times v divided by the magnitude of u times the magnitude of v. And again, just kind of going back through here, if I have two vectors, actually, let me just kind of do this actually up here. So remember, orthogonal is going to be if they're right? So if I have the u dot v is a positive, then we're going to have two vectors in the same direction. And if I have them in opposite directions, not necessarily in exact opposite directions, so that one would be negative. Oops, I'm saying u dot v would be a negative. So let's just call this one u, and that's v. So again, you can kind of see this scalar. What the dot product does is it produces a scalar, and it tells us kind of how these two vectors are going to be related, at least that scalar multiplication of each other. And again, if it's positive, they're in the same direction. And then obviously if it's 0, then they're orthogonal or perpendicular. And then negative, meaning they're going to be in opposite directions. So we can go a little bit further with the dot product to actually identify what that angle is between those two vectors. And that's just going to be using this formula right here. So again, it's a good problem, at least for my students. They get to practice applying the dot product, the magnitude, as well as using the cosine inverse. But we don't get into too much detail as well, with the formulas, or at least deriving the formulas. Just kind of one of those, I want them just to kind of be getting used to everything. So now we just kind of get into the general idea of that parallel and orthogonal vectors. So if two vectors, u and v, are orthogonal, that means the dot product, u dot v, and again, a lot of times I want to make sure this dot is going to be nice and thick for the students, u dot v is going to equal to 0. So that scalar product is going to be 0. Now, if the two vectors are parallel, then the dot product is either going to be or the angle between them is either going to be 0 or 180 degrees. So if the angle is 0, now again, these are just kind of vectors that are not in component form. Obviously, if they're in component form, they'd be right on top of each other. But you can see if they're two angles like u and v have 0 in between them, then it's obviously the exact same vector. They're pointing in the exact same direction. And then if the vectors have 180, you can see that they're going in opposite directions. But we're considering them parallel because at least the slopes are going to be the same. All right, so that's kind of how I started with the students. I said, all right, let's go ahead and just find the vectors or find the angle between the two vectors and then determine if they are orthogonal, parallel, or neither. Now, I did allow the students to first apply the dot product, and therefore, if they identified the dot product to be 0, like in the first example, then they could just justify that the angle between them is 90 degrees and that the two vectors were orthogonal. So in this first example, the first thing we did was find the dot product, and therefore you can see we got it to be 0. And again, if you look at this formula, like go back to the formula, you're going to have to identify, not that one, this one, you're going to have to identify the dot product anyways, and then the magnitude of u and v. So you might as well do the dot product first. If you get 0, then you're going to know that they are, that they're going to be orthogonal. Now this next example, I do the dot product, right? So now I have w and t vectors written as a linear combination. And however, when I do the dot product though, I get negative 51. So that doesn't tell me enough information at this moment to determine if they are parallel or orthogonal. Well, I'm sorry, they're not orthogonal. So I don't know if they're parallel or not. So then what I'm going to do is I'm going to continue with identifying the magnitude of w, which is going to be the first component squared plus the second component squared, so which is square root of 104. And then I do that again for t, which gives me the square root of 26. So now I plug them all into this formula for the cosine of theta equals there. And then when I go ahead and simplify this, I get -1. And again, like you could type this in your calculator if you want to, but again, really what we're looking for when we're doing these two vectors, if we're determining they're parallel or negative, like, 0 or 180 degrees, we're going to be looking for cosine of theta to equal -1 or for it to equal +1. And you can see in this case, since cosine of inverse cosine is equal to -1, we know that angle is going to be 180 degrees. So therefore, we can consider these two vectors to be parallel. And then what I did is I just gave the students some more examples. I said, all right, let's go ahead and practice some more and kind of see how you guys do. So I gave them these two, as well as these two vectors as well. So let's just go ahead and work through these. Again, the first thing I like to do when doing these problems is just to apply the dot product. And again, if you kind of get stuck sometimes, you can always label them as their components. Okay, so this is U1, U2. This is going to be V1, V2. And again, a lot of students want to go ahead and write this as a vector. So just be careful. Use parentheses. When you're applying the dot product, you're looking for the scalar, not a vector. So this is going to be -2 times 6. So therefore, that's going to be +12 minus 12, and you can see 0. So again, right off the bat, we're getting 12 minus 12 is 0. So therefore, we can say that U and V are orthogonal. Or we'll just write orthogonal. So on to the next problem. Again, first thing we're going to want to do is identify the dot product. So I'm just going to do C dot D. And that's going to be, again, the first component, 6 times -3. Now, again, some people don't like using the I and J. So again, if you want to write this in component form, go ahead. Like, that's fine if that makes it easier for you. So I'm going to multiply 6 times -3, and then I'm going to add that to the product of 5 times a -5/2. Okay. And when I go ahead and do this, let's see, I get this to be a -18, and this becomes a -25/2. Now that doesn't look very nice to go ahead and complete. Now obviously I could go ahead and multiply. I could rewrite this as a fraction. But again, I know that at least it's not going to give me 0. So if I was just to go ahead and rewrite this, let's see, I could rewrite this as a -36 divided by 2 minus 25 over 2. And therefore you can see that, right, I can write -18 as -36 over 2. Sorry, I didn't mean to do that. And therefore, then I would have a -61 over 2. Okay, so that's going to be my dot product, which obviously is not going to be orthogonal. Now, the next thing we're going to want to do is identify the magnitude. So let's just go ahead and find the magnitude separately here. So I'm going to have the magnitude of C. So the magnitude of C here is going to be, let's see, it's going to be 6 squared plus 5 squared. So 6 squared is going to be 36 plus 5 squared is going to be 25. So therefore, that's going to equal the square root of 61. And then for B squared, or I'm sorry, the magnitude of B, that is going to be the -3 squared plus, let's see, that's going to be a -5/2 squared. Okay, and that's going to be the square root of 9 plus 25/4. All right. Now, again, some students are like, all right, that looks kind of confusing here, 25/4. But again, we can type all this stuff into our calculator, right? Like when we're using a calculator, because that's what we're going to have, my students will have access to this for a calculator. We can just go and type this all into a calculator. So I have cosine of theta is going to equal a negative 61 over 2, which you could easily divide, right, as 30.5, divided by the product of the square root of 61 times the square root, and again, that's not the dot product, but it's multiplication, 9 plus 25/4. And again, that's what I'm just going to be typing into my calculator because I just want to avoid, writing down any kind of or any kind of decimals into the calculator. So I'm going to take a negative 61 divided by 2. And we're going to divide that by the quantity. And again, you want to make sure when you're doing this, when you're typing this in your calculator, make sure you put the denominator in parentheses. So that's going to be the square root of 61 times the square root. And again, your calculator will follow order of operations here. 9 plus parentheses 25 divided by 4. Okay, so I'll close a parenthesis there, and then I will close the parenthesis of the denominator. Open, open, close. And I get -1. Interesting. Well, again, remember, if cosine of theta is equal to -1, that means those vectors go in opposite directions. So therefore, the angle between the two vectors, so therefore theta is going to equal 180 degrees, right? If you have your vector, sorry, let me just go and draw this real quick. If you have 180 degrees, you can see that these vectors are going in opposite directions, right? So therefore, we have a vector, there's going to be -1. So you can see they're going in opposite directions. So therefore, these are considered parallel. Okay, now let's go back into red. All right, next example. Again, we have another linear combination. So I'm going to go ahead and follow through on this. In this case, we have A and B. So I'll go ahead and do the dot product. What do I want to do? So the dot product, so that's going to be A dot B. So that's going to equal 7 times -2 plus 2 times -7. And therefore, we look like we have -14 minus 14. So it looks very promising, but this actually gives us a -28. So it's not going to work in this case. Then the next thing we want to do is go ahead and identify the magnitude of A. So the magnitude of A in this case is going to be the square root of 7 squared plus 2 squared. And hopefully you recognize that the magnitude of B is going to be exactly the same, because if you think about this, it's just negatives, right? And you're squaring the negatives. So that's going to be -2 squared plus -7 squared. So again, 7 squared is what? 49 plus 2 squared is 4. So therefore, that'll give us the square root of 53 and the square root of 53. Now, when I want to find this angle here, I'm going to have the cosine of theta is equal to -28 over square root of 53 times the square root of 53. Now, let's think about this for a second. The square root of 53 times square root of 53 is just going to be 53, right? So therefore, I can also rewrite this as the cosine of theta equals -28 over 53. Therefore, theta equals, and again, this is going to be something, theta is going to equal the cosine inverse of -28 over 53, which equals, I don't remember, so I'm going to type it in, -28 divided by 53, cosine inverse of that answer is going to equal 121.89 degrees. Okay, so you can see that's going to be the angle of those two vectors, which makes sense, right? They're pointing away from each other because our dot product is negative. And again, that works as well. In this case, you can see that these two vectors are pointing away. You can see the dot product is a -1. Now, the next one, again, I have some fractions. Now, in this case, I'm going to do a little bit of a trick that we can follow. And I'll show you 2 steps that you could do here to make this problem a little bit easier for you, depending on what the question is. Now, the first question I want to tackle is let's just identify the dot product. I think with the dot product, we want to be able to, again, the dot product is giving us a scalar. So we want to identify this dot product and just make sure we can do this even if we have fractions. That should not be changing our answers or as far as what we can do here. So in this case, we have 1/2 times 2, that's going to be 1. And therefore, this is going to be a negative 3/4 times negative 3. Let's see, that's going to give us a positive 9/4. Now, if I combine that, the 1, I could rewrite that as a 4/4 plus 9/4, and you can see my answer is 13/4. Okay, so without using a calculator, just knowing my fraction operations, I can identify this dot product. Now, when it comes into identifying the angle between the two vectors or determining if they are, orthogonal, I know they're not orthogonal, I'm sorry, determine if they're parallel or not, I'm not going to, want to do calculations with these fractions. Even though I have a calculator, it's still a lot. Nor am I really going to want to plug them into my calculator or use decimals or anything. So there's one thing I just want you to think about. Two kind of things we can do. First of all, if we're looking at two vectors, and if we're trying to identify like the angle between the two vectors, if I use scalars of these two vectors, you can see that the angles don't change, right? If I shorten a vector or lengthen a vector, it's still going to give us the same vector. So one thing we could do is instead of using the angle between u and v, why don't we use the angle between u and 4v? Because if I multiply this by 4, I'm going to have 2 minus 3. Now I'm not dealing with any fractions. It's a lot easier for me to be able to work with this, okay? The other thing you can see is, again, like when things are parallel, yes, you can see that they're pointing the same direction or pointing opposite direction, like the angle between them is 0 or 180 degrees. But that's a lot of work to identify if things are parallel or not. What I prefer to do is also just look at the slope, right? Remember, the slope is going to be the rise over run. So if I have negative 3/2, now obviously you see once I transfer this, what the slope is, but negative 3/2, that needs to be equal to negative 3/4 over 1/2. Well, again, this is just a fraction over fraction, right? So multiply by the reciprocal. Oops. So I have 2/1 over 2/1. And guess what? That's going to equal a negative 3/2. So without actually having to calculate the answer, and again, if you need to figure out the angle between them and you have fractions, I would use that scalar and use the calculations with that rather than dealing with the fractions. You can obviously do the fractions, but it just makes up for more opportunities to make mistakes. So that's what I'd recommend you do, is look for, when you only have one fraction like this last example, it's not the end of the world. It wasn't bad, but you could have done the exact same things I just explained here up here, and it probably would have been a lot easier now that you know. But I wanted to show you how you could work through that example, even if you have fractions, by using your calculator. But again, a lot of times just look at, using scalars of their vectors to avoid the fractions. Again, this works in this case for the angle because it's not going to impact it, as well as, just identifying if they're parallel or orthogonal. All right, so that was kind of our applications of the dot product. That's about as far as we went with that. And then we're going to get into some tips for doing word problems. Now, a lot of these problems are actually going to be from our last section when we were just kind of talking about vectors. But I just wanted to kind of explore them a little bit more in this section rather than the first section, because the first section was just like a lot of content. So when we want to identify like word problems using vectors, the first thing we want to do is draw a picture and label all its parts. Then what we want to do is identify the vectors provided and that are needed to solve. So, whatever we're kind of looking for, we want to make sure we understand them. And the last thing is we want to define our variables and set up any equations. And then last but not least, we want to solve and check our solution. Basically, checking your solution is not like checking your work, but checking to make sure your solution makes sense. So the first word problem that I did for my students, or at least I went through step by step for them, was talking about an airplane is flying across country due east. So it's going due east at 323 miles per hour. So you can see here, I represented this as a vector going due east, 323 miles per hour. And there's an air current at a bearing of 60 miles per hour. So I represented this bearing here at 60 miles per hour, at a bearing of 60 degrees at 15 miles per hour. Now, the question was saying, what is the actual speed and bearing of the airplane? So what we got to do is kind of think I gave my students this understanding that, that they could relate to, when you're outside and you're running and you feel like wind at your back, you're going to start running faster and you actually are going to be going faster, right? And the contrary, if you're running, you get this big gust of wind going against you, that's going to be slowing you down. You're going to have to work harder. So if we're trying to look at what is the final thing of the plane. Now, again, this is the plane that's not correcting. And I know for the physics students, we're not taking in any kind of resistance or gravity or all those other things. We're keeping things very, very simple for this lesson. But if I have an airplane that, is heading out in this direction at this speed, and this wind is able to affect the airplane at 15 miles per hour at a bearing of 60 degrees, what is that going to do to the airplane? Assuming it's not like self-correcting or anything. Well, what we're looking for is really the airplane plus the wind, right? Because we need to take into account the airplane as well as we need to take into account the wind. Now, I didn't write this up here, but I should do this. So what we're going to do is we need to take into account the magnitude as well as the angle of each of those components. And that is a component that we worked on in our last class period, that at least we explained, as any vector can be represented by its magnitude as well as its angle. So what I did is I say, all right, so I'm going to have the airplane. I'm going to represent that as vector A. So you can see it right in here. It's going 323 miles per hour at an angle, at a bearing of at an angle of 0 degrees, right? Even though that's a bearing, it's going due east. But remember, your calculator, which we're going to be using, your calculator only understands standard form. So even though the problem's in bearings, we have to make sure, like, yes, that's 90 degrees bearing, but that's 0 degrees standard form. So it's going to be cosine of 0, sine of 0. Now, the nice thing about that is that gives us a unit vector, 1, 0, right? And you can easily distribute the 323, distribute there to give 323, 0, which makes sense, right? You're going to have, if you're represents the vector, it's going to be 323 horizontal and nothing up or down. Now, as far as the wind goes, I didn't plug in 60. Instead, I plugged in 30. And again, this is very important because the bearing is 60 degrees. That's from due north to here is 60 degrees. But again, our calculator is only going to understand this in standard form. So from here to here is 60. That means from here to here is going to be 30 degrees. So that's why we got to make sure we're using 30 degrees as our angle. Now, again, the wind is 15. So what I do is I calculate. Now, thankfully, 30 degrees is on the unit circle. So that's going to be square root of 3 or 2, comma 1/2. And then you're going to distribute the 15. And you get 15 square root of 3 divided by 2, comma 15 over 1/2. And again, you could convert those and store them and stuff like that. But I wanted you to see, what is it we're looking for? And again, we're looking for this magnitude. Here's this equation that I was talking about. We want to find, actually, I don't know why I wrote that like so far away. What we're looking for here is A plus W, right? So A plus W is going to be the airplane plus the wind. So when you add the airplane plus the wind, you're going to get this vector. Now, again, since we have the square root of 3, this gives us a irrational number. So therefore, I stored this as alpha A. And again, you don't need to store this. You can pretty much probably use the answer or at least write down the multiple digits and you'll probably be okay. But I wanted to store it just because, one, it's a lot faster to type this into my calculator once it's stored. So therefore, I found the magnitude of my A plus W. And again, you could give this another name like V if you wanted to, or R as resultant vector. But again, this is going to be square root of first component squared plus second component squared. And then that gave me 336.07 miles per hour. Now again, I want to stop. Does that make sense, right? If you're traveling 323 miles per hour and you have wind at your back pushing you forward, not 100%, not like directly behind you, but at an angle, then it makes sense you're going to go faster, right? But not all the way, an extra 15 miles per hour faster because it's at an angle. So 336 degrees miles per hour makes sense. And then in the same respect, we have the angle of the vector. And we ended up doing the angle. I do tangent inverse. Or sorry, I should probably write that in there. Just because some students still get this wrong. So theta equals tangent inverse of 7.5 over A. Okay, so theta equals tangent inverse of 7.5 divided by my stored answer A. And that gives me 1.27 degrees. Now, again, that's not the bearing. So what I did to find the bearing is I subtracted that from 90. So I did 90 degrees minus 1.27. That's how I got my bearing. Right? Because again, the 1.27 is just giving you this angle down here. Very, very, very small. Now again, that's a really, really small angle, but doesn't make sense. Like you're going 323 miles per hour. That's really, really fast. And there's only a wind at 15 miles per hour. So yeah, it's going to take you off course, but you have so much speed going horizontally, it's not going to take you that much off course. It's not going to take you that much off course from there. We're only at 15 miles per hour. So that's how we went ahead and solved the problems using vectors. Then we kind of went into, just on one of the students, a lot of students have trouble with this, is writing the expression of writing an expression of an equation using a vector. So that's what I wanted to help students out with this. And I did ask them also to sometimes draw a picture, and I think I might have a little bit. I'll try to fit in some pictures here. So this one, a boat is traveling at a bearing of 263 degrees. So what we're going to do is we're going to have a boat 263. So that's going to be down there. Right? That's the bearing. Now again, that's going to be 30 miles per hour, but that's not the bearing that's not the angle in standard form. So an angle in standard form here is from there to there. So again, if this is 263, then that means this has to be what, 7 degrees? So therefore my angle is going to be, so that's going to be 180 degrees. So it's really, really important. Let me actually change that up. There you go. So you can see from here to here is 7 degrees. From here to here is 263 degrees, but that's the bearing, right? Well, again, when we're using our calculator, we can't use the bearing. We have to use our angle. So therefore, this is the standard form is going to be 187. Sorry, that's the angle. How far am I traveling? 35. So it's going to be 35 times the angle cosine of 187. Oops. 187 degrees, and then the sine of 187 degrees. And again, I didn't want students to actually solve this. I just wanted them to practice setting up the equation. And that you can see when I did the word problem, that's the first thing I did, right? I found the vector for the airplane, and then I found the vector for the wind. So it's a really, really important thing to be able to take from the word problem what your vectors are going to be. The next one says a plane is traveling 300 miles per hour as it begins to descend for a landing at an angle of depression of 15 degrees. Now, again, we understand an angle of depression is going to be an angle below the horizontal, right? So we have a horizontal, and then we have an angle of depression. So that means the angle is going down. So again, if we wanted to think about this in terms of like standard form, we want to make sure that we're going to represent this as a negative, right? Because like, even though this is north, like if you're going down, you can see like my y, like that's going to be representing the plane in a downward direction. So we have 300 miles per hour. And then we're not want to use positive because positive would be giving us a, x and y that would be both positive. We want to represent that y coordinate to be negative. So therefore, I'm going to use cosine of negative 15 degrees and the sine of negative 15 degrees. All right, the next one is a cart full of children is being pulled up a ramp at an angle of elevation of 2.5 degrees. So again, now we have like a nice little ramp. And again, some people did really, really well with drawing a nice cart full of children. I'm not going to do anything special, but there we go. I have a children and they're being pulled. Okay. But this angle of elevation here is going to be 2.5 degrees. And then the force is going to be 4 pounds. So in this vector, again, since it's an angle of elevation, we want that to be positive. So therefore that's going to be 4 times the cosine of 2.5 times the 2.5 degrees, and then the sine of 2.5 degrees. All right, and then lastly, we have a rope is being horizontally pulled by a truck due west of a car stuck in a ditch with a force of 1,500 pounds. So again, that due west is telling us, all right, there's this horizontal pull, right? And so here's a car, car stuck in a ditch, and it's being pulled by a truck, right? So, there's the truck going in, pulling the truck westerly, right? It's in a ditch. Now, again, we need to understand that that has a force of 1,500. And again, like what is the angle? Like how do we represent this horizontal, this west angle? Well, that's going to be used, if we were to think about this, like what is this force on the car? That's going to be an angle of 180 degrees. So we can say 1,500, and that's going to be times the cosine of 180 degrees, comma, the sine of 180 degrees. All right, so then when students got a little practice with setting up the vectors, we ended it off with one last word problem. And again, it's another practice with the bearings. So in this example, a boat is traveling at a bearing of north 33 degrees west. And right there, I just kind of told my students, all right, let's just stop and let's draw that boat, right? So we have north 33 degrees west. So that's going to be somewhere right around there. Okay. And there's the angle. That's going to be our 33 degrees. And then it's going at 42 miles per hour, right? So that's going to be the magnitude of the vector. Then there is a current against the boat at a bearing of south 17 degrees east. So now I have a new bearing. That's a bad bearing. Let's try that again. Okay. Now again, this new bearing is going to be south 17 degrees east. So I'll try to do my best here. Okay. So it's a nice little small angle. That's going to be 17 degrees. And that only has a magnitude of 12. So you can see how like my picture now is kind of getting a little difficult to understand, right? It's kind of like pretty small here. So what I'm going to do is I'm just going to kind of now represent these kind of offsite a little bit. So I'm going to say, all right, the boat here, let's just talk about this. The magnitude of the boat is going to be, is 42 degrees or 42 miles per hour, sorry. The bearing of the boat is 33. But again, we don't want to deal with the bearing of the boat. We want to deal with the angle of the boat. So the angle of the boat is going to be 90 plus 33. So that's going to be 123 degrees. All right. So from this picture, I can kind of see where that's going. Now let's talk about the current. So the magnitude of the current, that is going to be the speed of the current, and that's going to be 12 miles per hour. That kind of looks a little difficult to visualize. So let's space that out a little bit. Okay. And then the angle of the current is, again, you got to think that's going to be from standard form, right? So you could do the positive version or you could do the negative version. Now, in this case, I'll do the positive version. I think in my class, I actually did the negative version and some students kind of got confused with that. So I'm going to do the positive version. So all the way around, 3/4 of way around circle is 270. So if you just add 17 degrees, that's going to give you 287. It doesn't matter if you use 287 or if you go ahead and use a negative 83. Typically, it's a little bit easier to use the acute angle. But again, I don't know. But again, you could use the negative or you could use this obtuse angle. So now we have our components for the boat and we have the components for the vector or for the current. And now we can write a vector for each of them, right? So B, which is going to represent the boat, can now be represented as a vector in terms of its magnitude and its angle. And the current can be done in the exact same way. So the current can be written down as 12, the magnitude. Oops, I'm sorry, current. So it's going to be 12 times the cosine of 287 degrees times the sine of 287. Now, I will say that none of these are going to be some nice numbers. So I am going to be storing these all in my calculator now. So what I'll do is I'll show you how I stored them. Let me actually give myself a little bit of room here because what I'm going to do now is go ahead and just figure out what I want to do now is just kind of figure out the magnitude of these two vectors. And therefore, then we can identify what is it we're looking for. So to identify the component form here, I'm just going to distribute that 42. So I'm going to do 42 times the cosine of 123. And that's going to be a negative 22.878. So I'm just going to call that alpha A. Oops, I'll store that as alpha A. Oh, come on. So store alpha A. There you go. So when I do the component form, that's negative 22.87. And again, I'm not going to use the rounded answers. That's why I'm storing that. And then if I do 42 times the sine of 123, and then I'll store that as alpha B. Now, again, you could type this a lot and a lot more of this stuff in your calculator, but I just want to kind of show my steps where I'm getting some of these numbers. So therefore, you can kind of check with me. And again, I'm storing this as alpha A, and I'm going to store this as alpha B. It's a lot faster and easier to write them as their stored answers than trying to explain to you, all these decimal points again. So again, now to get the next one, I'm going to do 12 times the cosine of 287. So I'll do 12 times the cosine of 287. And that should be a positive number, which it is. And that's going to be 3.51. Okay. And I will store that as alpha C. And then we have 12 times the sine of 287, which should be a negative number, which it is. And that is going to be, let's see, negative 3.1, negative 11.47. So just let me get that out. So that'd be 11.47. Okay. All right, and then I'm going to store that as alpha D. Okay, now it's not really necessary to store all these. Again, the only reason why I'm doing this is just so you can kind of follow along with me. I think when I did these in my class, I didn't store them. I just typed more of this in. I just kind of typed everything into my calculator, just kind of as they were. But I want you to understand, so there's the component form, because there's different operations we could be asking for this, for these. But in this case, it says determine the final speed and bearing of the boat. So again, what we want to do is like identify what is the speed of going to be the boat plus the current, right? Now, again, in this case, the current is going against the boat. So we should expect here that this boat is going to be going slower, right? And also it's not going to be going as far west, right? It's kind of getting pushed back to the right a little bit, or a little bit more farther east. So if I want to identify, A plus, what I'm going to do to identify A plus, sorry. If I want to identify the speed, what that's going to be is that's just going to be the magnitude of B, vector B plus vector C. Okay? So all I'm going to do in that case, as far as writing that out, is that's just going to look like this. So that's going to be the square root of, again, if I want to find these components, that's going to be of A plus C, quantity squared, plus B plus D, quantity squared, right? You're basically combining these two vectors. So let me just kind of write this down here. B plus C is equal to the vector A plus C and B plus D. So that is my component form of that vector. And again, I'm not going to store that again. I just wanted you guys to kind of see what that was so we could kind of just take a break here and calculate those. So let's go and figure out what A plus C is. So I'll do alpha A plus alpha C, square that. And then I'm going to add that to alpha B plus alpha D and square that. Then I'm going to take the square root of that, and I get 30.64. Now, again, we want to make sure of this. Like, does this make sense? 30.64. Originally, it's going 42 miles per hour. But with the current against it at 12 miles per hour, you can see it's slowing down all the way to 30.64, which makes some sense, right? I mean, because it's almost, it's slowing it down a lot. It's coming basically almost, direct at it. So you can see like that makes some sense as far as how it's slowing down. Now, then I also need to figure out the bearing. Now, again, it's very important when we're figuring out this bearing, we need to look at this vector here. So when we figure out the bearing of this component form, it's going to give us this angle, okay? Because again, remember when we're doing the tangent here, tangent of theta, again, that's going to be B over D divided by A plus C. And that should be a negative angle. So I'm going to do alpha B, oops. So I'll do alpha B plus alpha D divided by alpha A, oops, parentheses, alpha A plus alpha C, close parentheses, and then tangent inverse of that answer, and I get negative 50.8, and that's correct. But again, that's only giving me, come on, almost done. So that's going to give me a negative 50.8 degrees. Now again, that's going to be from standard form to down there, right? So it's very important for me to understand though, that's not the bearing. The bearing is always again going to be from due north. Well, actually, sorry, I should take that back. If I have that as negative 50.8, again, my bearings, we're not dealing them from bearings, we're doing them from south. So if my bearing from here, from standard form though is negative 50 degrees, if I want to find the bearing, So again, we have negative 50 degrees, right? So there it is. That's negative 50.8 degrees. All I want to do is figure this out. So to figure out that angle, I'm just going to do 90. Get them right on space. 90 minus 50.8 degrees. So when I do 90 minus that last answer, I get 39.19. So it has a bearing of 39.19 degrees. And again, that's what we're looking for right there. That's where the 39 degrees is. And again, sorry, it's going to be south 39 degrees east, 39.9 degrees east. And again, all I'm trying to do is match up the bearing with the same notation that the bearing was provided. You could also do the bearing from due north, but since our bearing was originally in terms of like the north, the cardinal system, the compass headings, therefore that's what I'm going to use first. I'm going to use south 39 degrees. So it's south 39 degrees, 39.19 degrees east. And therefore, again, you can see how I stored them. Again, you find the vector of the boat, the current, you add those components up to get your resultant vector. And that is going to be in terms of the boat, the speed of the boat plus the current. This time the current is working against us. So therefore, to find the speed, you just identify the magnitude of that resultant vector. And then to find the angle, you go ahead and use the tangent, but you just need to understand the context of where the tangent is given us. And therefore we need to convert our answer to bearings, which we go ahead and do. And that was it, ladies and gentlemen. I hope you learned some things about vectors, as well as how to apply them for the dot product to identify the angle between two vectors, as well as some word problems. And if you do have any questions, feel free to leave them down below. I do my best to always answer them, or hopefully some other people in the community will be able to help you out as well. So I look forward to seeing you on the next lesson. Cheers.